Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Inshallah, today me and my group member will be presenting about the electric potential that we have already learned in chapter 24. 24.1 Electric potential and potential difference. Electric potential, or also known as voltage, is actually a physical quantity that only depends on the source charge distribution. The value of electric potential will be exist at all points in an electric field. Since the value of electric potential will be different at every point, there will be potential difference between 2 points A and B. So, if the charge is moving between 2 points, we can have the potential difference by dividing the difference of electric potential energy by the charge itself. Another formula to calculate the potential difference is by inserting the formula of the difference of electric potential energy into the previous formula. As we can see here, we can cut out the Q, and what's left is only this equation to find the potential difference. This equation shows us that potential difference also has units of electric field times distance, which means the SI unit of electric field can also be expressed in volts per meter. What can we conclude here is the electric field is a measure of the rate of change of the electric potential with respect to position. The situation in the electric field is similar to the situation applied in the gravitational field. For example, when an object was placed here, there will be gravitational force acting on it. The force will be pulling the object downward and create a displacement. When there is a force and there is also displacement, we will have the work done by the object. The work here can be defined as internal work since the force acting on the object is the gravitational force. The same situation was applied when the charge is entering an electric field, which will bring us back to these equations. The difference of electric potential energy will be negative because the test object will be moving from the highest potential energy to the lowest potential energy. Now, here is the charge that moving to the right. The voltage will be decreasing along the electric field, which causes voltage at the point B will be lower than the voltage at the point A. To move the charge in constant velocity, we must apply the exact same value of force, but in the opposite direction. That is why the work external will be equal to the opposite of work internal.
Assalamualaikum, my name is Fatin Natrah, binti Mazelan, and I'm going to explain on subtopic 24.2. What is uniform electric field? A uniform electric field is a field in which the value of the field strength remains the same at all points. A constant electric field can be produced by placing two large flat conducting plates parallel to each other, like can be seen in the picture. Since the field lines are parallel and the electric field is uniform between two parallel plates, a test charge would experience the same force of attraction or repulsion no matter where it is located in the field. Field lines always point from regions of high potential to regions of low potential. In a uniform electric field, the equation to calculate the electric potential difference is super easy, which is V equal to negative ED. In this equation, V is the potential difference in volts, E is the electric field strength in newtons per coulomb, and D is the distance between the 2 points in meter. But in general, we usually neglect the negative symbol. What about potential energy in uniform electric field? How does potential change over a uniform electric field? So, if a positive charge moves from point A to point B, the electric potential energy of the system decreases.
24.3 Electric potential and potential energy due to point charges.
Firstly, we will see the electric potential due to a point charge, where given formula is V equal to KE times with the Q over R,
We can also obtain the electric potential resulting from two or several point charges by applying the superposition principle. That is, the total electric potential at some point is the sum of the potential due to the individual charges. So in this formula, Ke is a column constant, Q is the charge. Remember to include the sign because V is a scalar quantity and R is distance in meter. In example 24.3, we need to determine the total electric potential at point P. So we can apply the formula just now to find the electric potential at P due to charge Q1 and Q2, which is the algebraic sum of the potentials due to the individual charges. We can use theorem Pythagoras to find the distance of Q2 from point P, which is 5 meter. Hence, substitute all the value into the formula to get the final answer is negative 6.29 times 10 to the power of 3 volt. Now, imagine that an external agent brings a charge Q2 from infinity to point P. There is work that must be done to do this, and this would represent a transfer of energy across the boundary of the two charge system, and the energy appear in this system as potential energy when the particles are separated by a distance r12. Therefore, the electric potential energy of a pair of point charges can be found as UE equal to Ke times with the Q1 times Q2 over R12. If the charge are in the same sign, then UE is positive. Positive work must be done by an external agent on the system to bring the two charges near each other, while if they are in opposite of sign, UE is negative. Negative work is done by an external agent against the attractive force between the charges of opposite sign. If the system consists of more than two charged particles, we can obtain the total potential energy of the system by calculating UE for every pair of charges and summing the terms algebraically, like this formula shown here.
Moving on 24.4, obtaining the value of electric field from the electric potential. In this subtopic, we're going to learn how to find the electric field if only we know the voltage in certain region. So we're going to rearrange the voltage equation, and we're going to get electric field is equivalent to negative delta voltage delta V over delta X. So from this equation, we can get the slope of V against X can determine the magnitude of E on that particular distance. Next, the equipotential surface. Equipotential surface means the delta V along the surface is equivalent to 0. So how we going to get the delta V equivalent to 0? As we know, delta V is the dot product of electric field and the distance. So the dot product we're going to produce cos theta. So cos theta, so cos 90 we're going to produce 0. So if cos 90 0, so the delta V will be equivalent to 0. So it indicate the equipotential surface is always perpendicular to the electric field because it will produce the delta V equivalent to 0. Equipotential surface of the in a plate, so this is the equipotential surface. It's always perpendicular to the E produced in a plate. So in at the point charge, the equipotential surface will produce a spherically symmetric electric field produced by a point charge. So in this equipotential surface, the work done by the charge will equivalent to 0. There will be no work done. So if the charge move from here to here, so there will be no work done. So moving on to the last subtopic 24.6, conductors in electrostatic equilibrium. So in equilibrium, so there is no moving charge. So if in every conductor there is a Gaussian surface in every conductor. This is the Gaussian surface, this is Gaussian surface, this is the Gaussian surface, and this is the Gaussian surface. At the Gaussian surface in the conductor, at the conductor, if it is in equilibrium, the electric fields in the conductor will always be 0. The charge reside on its surface, and the electric field is perpendicular to the surface of the conductor. Surface charge density is the greatest at the smallest radius of the curvature. So if it is irregular shape, the charge density will be more on the smallest radius. So in the if we have a sphere inside a spherical shell, so Q inside the shell will be minus to the Q inside the insulator or the inside the sphere. So that's all from us. Thank you.